Okay, till now we were discussing in the lecture online the instructions set. Some of the classes now I'll take offline like this. I'll record the lectures and send you the link. You can just go through them and then we can discuss it in the class so that we can quickly finish the instruction set of 8085. So far we have considered only one particular group, that is data transfer group, and in that particular group the data is moved from one register to another register. No arithmetic or logical operation takes place, and in this case none of the flag will be affected because there is no arithmetic or the logical operation taking place. The data is simply moved from one register to another register. One of the register must be internal within the processor. The other register may be internal, maybe in some of the memory location, maybe in an IO device, and then the data is moved. We have considered 13 instructions in that particular group. 2 instructions, input and output, sometimes they are considered in data transfer group, sometimes they are put in the control group. So we'll discuss these instructions later on. Now the second group is the arithmetic group. As the name indicates, the instruction of this particular group are meant for arithmetic operation. There are only 2 arithmetic operations which are possible in this processor. One is addition and second is subtraction. And depending upon the source of the operand, you have several possible instructions. The very first instruction is add R. Add R, add is the mnemonic for the addition. It is the mnemonic for addition. And we already discussed one thing, that whenever 2 operands are involved in any operation, one of the operand must come from accumulator. So when we say add R, it means add the contents of accumulator with the register R and store the result back into accumulator. Now there is no need to specify accumulator. It is by default, it is supposed to provide one operand. The second operand may come from any of the internal general purpose register B, C, D, E, H, L, or it could be accumulator also. So the macro RTL of the instruction is add A plus R goes to A. The result is stored in accumulator. That's why it is called accumulator. It accumulates the result of arithmetic and the logical operation. Now, this instruction is a single byte instruction, and when it is executed, the first machine cycle is basically the output fetch machine cycle. And just like any other instruction, during T1, T2 and T3, the instruction code is read, and during T4 state, the instruction is decoded. We can write it like this. Now when the instruction is decoded, processor comes to know the meaning of the instruction is add R. Accumulator plus R should go to accumulator. Now both these registers are within the processor. No more reading operation is required. but only execution. Execution is possible like this. One of the operand is already in accumulator. The second operand from register R is moved to temporary register. And then the addition takes place in ALU, and then through internal data bus, result goes back to accumulator. Just recall this diagram. You have the bidirectional data bus, accumulator, you have temporary register. They basically provide two operands to ALU where the arithmetic and the logical operation takes place, and then through this internal data bus, result is stored back into accumulator. So first the second operand is moved from general purpose register to temporary register. Then addition takes place in ALU, and then through this particular bus it is stored, result is stored back into accumulator. And in this operation the flags are affected as per the result. We know that there are 5 specified flags: carry flag, parity flag, auxiliary carry flag, the zero flag, and the sign flag. We have already seen how these flags are going to be affected whenever arithmetic or the logical operation takes place. So, to perform this particular operation, this is not possible right at this stage. It needs few extra clocks. 2 more clocks are required. 2 more clocks are required. In one of the clock, the data from the internal general purpose register, it is moved to temporary, and in the other clock, the accumulator plus the temporary register, the addition takes place and the result is stored in accumulator. Now, rather than providing 2 extra states for this, just like move instruction, here also during fetch execute overlap, when it is fetching the next instruction externally, internally it can make use of the bus to execute the instruction like this, and therefore it can speed up the execution of the instruction. So internally it is executing this add R instruction, externally it starts fetching the next instruction of code. During T1 and T2 state, internal data bus is free. Only thing is, program counter outputs the address on address bus. ALE is issued. In T2 state, read bar becomes low, PC is incremented, and the external memory puts the information on the data bus. Every action is being taken externally, and internal data bus is free. So processor make use of this internal data bus to execute this instruction. From the calculation point of view, we can say only 4 states are required to execute this instruction. So add R, add accumulator with the register R, store the result in accumulator back. Single byte instruction, and there are 7 variations possible. And the flags are affected as per the result. Just like this addition operation, there are few more addition instructions. The second instruction is add M. Remember, just like move A to M or move M to A, wherever M appears, it means there is an operand pointed by HL register pair. So the meaning of the instruction is add the content of accumulator with the memory pointed by HL register pair and store the result back into accumulator. This is also a single byte instruction, but no variation. And what happens, how this instruction is executed? First machine cycle is the output fetch of 4 states. So the code is read and decoded. And now the instruction is to be executed. So first, this operand, which is available in a memory pointed by HL registered pair, is read. So a second machine cycle is executed, which is memory read machine cycle. And this is of 3 states. Now in this machine cycle, what happens? The data from the memory is read and it is moved to temporary register. In T1 state, HL register pair outputs the address. In T2, read bar becomes low and external memory put the data on data bus. In T3, when read bar goes high, data from that data bus is moved to temporary. And now execution takes place. For execution, accumulator is having one data, second data is in temporary register. This operation takes place and result is stored in accumulator. This action takes place during fetch execute overlap, because this does not involve the use of external buses, only the internal data bus is required. So from the calculation point of view, you can see 4 states plus 3, 7 states are required for the execution of this instruction. Similar to these two, there is a third instruction which is called add immediate data. Say, remember, the second operand may be present in an internal register. It may be present in a memory pointed by HL register pair. Second operand may be present in the instruction itself, and accordingly the addressing modes will be defined. It is a register addressing mode, it is a indirect addressing mode, it is immediate addressing mode. So the instruction is a 2-byte instruction, no variation, and the meaning of the instruction is add the contents of accumulator with the data byte present in the instruction as second byte and store the result in accumulator. So it executes output fetch machine cycle of 4 states, read the code, and after decoding it, it comes to know instruction is add immediate, which is a 2-byte instruction. So it executes memory read machine cycle of 3 states, and the second byte of the instruction is read and it is moved to temporary register. So second operand is now in temporary. During fetch execute overlap, accumulator plus temporary, this operation takes place and the result is stored in accumulator. Any time an addition takes place, flags are affected as per the result of the addition. If there is a carry from MS bit, then carry flag is set. If there is a carry from B3 to B4 bit, auxiliary carry is set. If the sign of the number is 1, sign flag is set. If the result is all bit 0, 0 flag is set. And if the number of ones in the result is an even number, then the parity flag is set. These three addition operations are your simple 2-byte addition. But if you want to add, let us say, a multi-byte addition, you want to have multi-byte addition. Let us say you have a 3-byte or maybe say 4-byte data. You want to add these two. Certainly first you will add the least significant byte. It may generate a carry. Then this carry is added to these 2 bytes. Result is, then it may generate a carry. All these 3 should be added. It may generate a carry. So there should be an instruction which takes care of the previous carry. So there are few instructions which basically takes the carry flag also into addition. And the first instruction of this type is ADCR, meaning is add with carry. So accumulator is added with the register R and the previous carry, and the result is stored in accumulator. It takes care of whatever is the previous carry, 1 or 0, that is taken into account in addition, and the result is stored. This operation affects all the flags just like normal case. So it's a single byte instruction, but it has 7 variations. Register R can be B, C, D, E, H, L and accumulator. So like previous case, you have output fetch machine cycle of 4 state. Instruction is decoded, and then during fetch execute overlap, this addition takes place. Method of operation is same. First, this particular register is moved to temporary, then accumulator plus temporary plus the previous carry, that operation takes place, and you can just keep in mind that ALU, it takes one data from temporary register, it takes another operand from accumulator, it also takes information from the flag register. All these 3 are taken together, addition takes place, result is stored, and the flags are affected. You can have the second operand in a memory pointed by HL register pair. So add accumulator with the contents of memory location pointed by HL register pair with carry, and then the result is stored in accumulator. First instruction is decoded, then the second operand is read from the memory, and then during fetch execute overlap the addition takes place. And the second operand may be in the instruction itself, add carry with immediate data available in the instruction as second byte. So accumulator is added with the data byte present in the instruction along with the carry and store the result back into accumulator. So these are the 6 addition operations. Second operand, one operand is always in accumulator, second operand is in either general purpose register, or it may be in a memory pointed by HL, or it may be present in the instruction itself as second byte. And then result is stored back into accumulator. All the flags are affected as per the result. Addition is with carry or addition may be without carry. So you have 2 different types of instructions possible. Now similar to addition instruction, you have few subtraction instructions. Just like addition with carry or without carry, you have subtraction with borrow and without borrow. And whenever subtraction takes place, again it is the accumulator minus the second operand, and the result is stored in accumulator back. First instruction is subtract R, meaning is subtract the contents of register R from the contents of accumulator and store the result back into accumulator. It's a single byte instruction and it has 7 variations: B, C, D, E, H, L and accumulator. So first the instruction is fetched and decoded. Once the instruction is decoded, processor knows the instruction is subtract R. Both the operands are within the processor. No more reading is required, only execution. Execution means first this register R is moved to temporary register, then accumulator minus temporary, this operation takes place and the result is stored in accumulator. Just like addition, these 2 actions take place during fetch execute overlap, and therefore no extra states are required specifically for this purpose. Internally it is executing the instruction, externally it is fetching the next instruction. So these 2 states will be counted in this fetch operation, just to know how much time is taken by this processor from one point to another point, or the time taken by a particular subroutine or program for execution. Second operand may be present in a memory pointed by HL register pair. So it is accumulator minus memory pointed by HL and the result is stored in accumulator. First opcode fetch machine cycle, instruction is fetched and decoded, then this operand is read in a memory read operation and it is put in temporary register, and then during fetch execute overlap instruction is executed. The second operand may be present in the instruction itself as an 8-bit data. So it is accumulator minus the data byte and the result is stored in accumulator. All the flags are affected. First, it fetches the code, decodes it, then it reads the second byte of the instruction, put it in temporary register, and then during fetch execute overlap, the instruction is executed. Similar to these subtract instructions, you have subtract instructions with borrow. So SBBR, it is subtract with borrow. The initial carry is taken into account. If you want multi-byte subtraction, then this particular one is required. So meaning is register R is to be subtracted from accumulator along with the initial carry or borrow and store the result back into accumulator. Back into accumulator, all the flags are affected as per the result. We have already seen that subtraction operation takes place internally by taking the 2's complement of this operand, adding it to the first operand, and the flags are affected. Whatever carry you may get, you have to simply complement and then store it. That is the correct value of the borrow or the carry, whatever you see. The second operand may be present in a memory pointed by HL register pair. And the result is stored back into accumulator. And the second operand may be present in the instruction itself as a data byte. So it is accumulator minus the data byte minus the initial carry, and that result is stored in accumulator. So just like 6 addition operations, you have 6 subtraction operations, instructions. 3 are with borrow, subtract with borrow, 3 are subtract without borrow. And in all these 12 instructions, the flags are affected as per the result. There are few instructions where quite possible all the flags may not be affected. So whenever you are writing a program, you will have to see whether the flag is affected or not in a particular instruction. The next instruction is increment R. See, there are few instructions, arithmetic operations, where only single operand is involved. Increment INR stands for increment. Increment R, meaning of the instruction is increment this register R by 1 and store the result back into register R. And store the result back into register R. This instruction is a single byte instruction and there are 7 variations possible. Increment accumulator, increment B register, increment C. Any register can be incremented by 1. This is also some sort of arithmetic operation, addition operation. That's why it is in arithmetic group. Now what happens in this particular case? The first machine cycle is output fetch machine cycle of 4 state, where the instruction is fetched and decoded, and now it is to be executed. Now since the register R is within the processor, no further reading is required, only execution. What happens? First this register R is moved to temporary register, and then this temporary register provides the operand to ALU. Internally it is incremented by 1 and the result is stored back into register R. Accumulator accumulates the result of arithmetic logical operations, but there are few arithmetic logical operations where the result is stored somewhere else. So whether accumulator is to be incremented or any other register, the data from that general purpose register is moved to temporary, and then temporary register provides the single operand to ALU. Within ALU it is incremented by 1 and the result is stored back into that register. Just like increment R, you have increment memory. Meaning is increment the contents of memory pointed by HL registered pair by 1 and store the result back into the same memory. Single byte instruction, but there is no variation. Operand is pointed by HL registered pair. Now how this instruction will be executed? Just think logically. First machine cycle will be output fetch machine cycle of 4 states. Instruction is fetched and decoded, and after decoding the instruction, processor comes to know it is increment M, increment the contents of memory pointed by HL registered pair. It means first the data should be read from the memory, because any AI operation takes place only in ALU. So a second machine cycle is executed, which is a memory read machine cycle